Yeah, so it was very nice talk about the data from the MIR, open code, everything, and there was a bit of touch of the evaluation, and you will find that some of the elements in my presentation are kind of repeating the same things, but from a slightly different perspective. And even though, so, okay, I do sound event detection and other kind of audio classification, but many of the things are common. So, okay, just a very basic outline. I will explain a bit about performance measurement, some kind of common metrics, how we define, interpret, how we use them, and then the big thing. So like what can go wrong? I will have one example evaluation for sound event detection and kind of a summary for evaluation protocols. So one first question is always like, how do you measure system performance? Like, what do you want to measure? So if it's kind of obvious that if you want to create a product for end users, then you kind of want your users to be happy with it. So you would want to measure the user satisfaction in one way. So this is a subjective measurement because it deals with people. Okay, this mean opinion score is not exactly used for the user satisfaction, but I chose this to give an example of kind of a subjective measure, which asks people, so how do you feel about it? So this mean opinion score, it's like for measuring media quality. So this most usually like a 5-point scale, excellent, good, fair, poor, bad. So then it's like, it does clearly have some problems. First of all, people will not use very much the extremes unless they are very, very certain something is like excellent. Then kind of like there is a bit of a dependency of the language and the perception of the scale. So what, how much difference there is between excellent and good? Is it the same amount like between fair and poor, or how does it go? So this doesn't sound like it would be easily reproducible. The other problem is, for example, that people get used to certain type of technology. So maybe if you repeat the same experiment, like 5 years later, what was excellent 5 years ago, it might be just fair at this moment. So this does not seem like the most reproducible measure. Okay, on the other hand, then we have the objective measurements. Okay, we're just going to use a mathematical formula. This is very clear. It does not depend on the user. So here comes the question. So what do we want to measure? Is this related to this kind of like happiness of the user of the product? How? But okay, at least this is mostly, it's close to being reproducible. Okay, so I'm assuming that everyone here does some machine learning. You have all had to train some system, then measure how well it works. So you are familiar with most of these metrics, which are used in pattern recognition. So accuracy, precision, recall, F-score, and so on. So all these are used to measure some classification performance. The choice of what you measure practically depends on what about the performance interests you. So this was mentioned also before, like what do you want to measure from it? I'm going in a rather general way with the presentation of them because this applies for any sort of classification problem. It doesn't even have to be audio. So, okay, practically the first thing that we do is we count how much a system will provide correct and wrong estimates. We compare the system output with the reference for some data that we have, like for our test data. And we count how many times they agree and how many times they don't agree. So true positives when the annotation is, a prediction is the same as the annotation. Then we have false negatives, true negatives, false positives, and so. After this, we just calculate whatever metric we want to use. We have the definition, it's very clear, no problem. Yes, so with classifiers, okay, whether classical methods or these newer neural networks, what we obtain at the output is some sort of a probability or likelihood that the test item that we look at belongs to the different classes. So we have a set of classes, and then we have some sort of probability that this item belongs to all the classes, like for each of them. In the ideal case, we have a probability of 1 for one class, and then we have 0 for all the other classes. Then we say, yes, this item belongs to this class. Of course, this actually doesn't go that way. So what we have at the output might be, it's with the neural networks, so it's a number between 0 and 1. So we have to decide where do we draw the line? What is enough that we consider it that, okay, this is now a 1. So this is this discrimination threshold. So with this discrimination threshold, we determine sort of a trade-off between correct and erroneous outputs. So, okay, when we have like a single class, like a single label classification, we assign one class to one item, so we can just look which of them has maximum probability, and that's the one. But if we need to decide, for example, like there's an audio tagging, or there are some I don't know, think an image that we want to classify that it contains people, buildings, cars, and trees, or audio file that contains violin, piano, and singing at the same time. So here we have to look at all the class probabilities. So then we need to put a threshold, like which of these classes we consider them that they are 1 and which are 0. Okay, so this is the operating point. This is the trade-off. So the one extreme case is that we accept as positive, as 1, any non-zero value. So we are sure that we find everything, all the items. All the true positives will be there, but then we also have the highest amount of errors because everything else is false positive. The other end is that no, not any errors, but also no true positives. So we are always somewhere in between. And I jumped a bit ahead of myself with this plot here with the ROC curves for 2 different classifiers. So in these ROC curves, we kind of see the proportion of true positives as a function of the false positives at the different thresholds. So there's one kind of method that, okay, we just like stop, we just set this threshold somewhere, and then we can evaluate the kind of metrics, or then we can use this ROC curve actually to characterize the system, and then we use the entire information. So the area under this curve kind of explains in one number the performance. So then the question is like, how much this operating point matters? Because for those metrics, like some of the metrics, it's important that we take a decision, because only based on this decision, we can calculate the count. So the true positives, the true negatives, and so on. So when we do the optimization of this discrimination threshold, we use some development set. So when we do the system development, we have this validation set, and we always look at the performance on this set. And then this is fixed. And then we have some other data that we test on, and then we just hope that it works the same way. So if they have similar distribution, it should, we hope. So in this category, we have, for example, accuracy, precision, recall, F-scope. Then, of course, we have the metrics which are independent of the operating point. So we have this receiver operating characteristic curve, which I just showed before, and then the area under the curve. So this looks at the different thresholds, and then we'll characterize the system over all of them. Then there is the log loss. So this is very much used recently in classification. So log loss or cross entropy is calculated directly from the probabilities. So there is no thresholding here. Everything just goes calculated directly. Basically, we are looking at the difference of between the output probabilities and the true probabilities. So, right. I just borrowed these formulas directly from the scikit documentation. So like you have probably seen them already there. The idea is that this log loss looks at how close the prediction probability is to the corresponding true value. So the true value is 0 or 1. And then we have this kind of a predicted, which is between 0 and 1. Yes, sorry. So yes, we deal with the 2 probability distributions. The reference has binary values. The estimated output has the values between 0 and 1. And when we have a lower log loss value, it means we have a better prediction. So kind of this is a measure of the uncertainty of the system. So a system that is correct and is very confident has a high probability on the correct class. So this will have a much smaller log loss according to a formula than a system that gets a correct answer but with less confidence. So this will have a smaller probability, so the difference will be bigger. And then a system which is very confident on the wrong answer gets penalized very much by this. Okay, so I have an example which will tie nicely to the upcoming interpretation of the metrics. So, okay, we have this sample. The true label for it is 1, and the predicted output is 0.9. So if we use a threshold of 0.5, we'll just say, okay, this sample belongs to class 1. So this is a true positive if we look at it this way. And if we look at it from the log loss point of view, we have a bit of a difference between the probabilities, and according to the formula we calculate, we get a log loss of 0.105. Okay, so then we have, for example, this other example, which is from true label is 0, the probability is 0.2. So with the threshold, this goes to the correct predicted class 0. This is going to be a true negative. The log loss will be 0.223. So this is kind of higher already. It's noticeably higher. And then when we have the third example for which the system gets it wrong, so it predicts like a 0.1, and if we do the thresholding, we would put this to the class 0. So this is then a false negative, and the log loss for it will be very high. So this is already 2.3. Okay, so if we calculate now some metrics on only these 3 examples, the accuracy here will be 66%, and the overall log loss will be 0.877. So it's for the accuracy, 2 out of 3 were correctly classified, and then for the log loss, we added up the values, and then we divided by the number of samples that we had, so by 3. So now what does this mean? For accuracy, kind of like, yes, 2 out of 3, that is like 0.66. But what is the 0.87? Does it mean anything? How does it help us? So yes, now about the interpretation of the metrics. What do you want to measure? This is what you should measure. For some metrics, this is very clear what the quantity means. So the easiest for here is the accuracy. Like if you have 10 items, you have accuracy 90%, clearly 9 of 10 were classified correctly. So 0, it's like everything was wrong. 100%, everything was correct. Random guess is 1 over the number of classes. So when you have 2 classes, the random guess is 50%. Obviously, you want your method to be better than that. Okay, same way, precision tells how many of the items marked as positive, they are indeed true positives. Then with recall, how many of the total number of examples were found by your system. So these metrics, they are kind of, they are meaningful for analyzing the performance just like independently. You can look at accuracy on the different classes in your problem and kind of like have an idea of how the system works. On the other hand, for area under the curve, this is mostly used for model comparison because, okay, like if you have area under the curve 0, this practically means that the system is like always wrong. If it's 1, it means that it's always correct. And then the 0.5, the halfway, this is the random choice. But then the values, the other values, they are not so clearly indicative of like what does it mean. So you use it for comparison. You have 2 systems, you calculate this number for them, and then you look, okay, which has it higher? So that is the better system from this point of view. Okay, and then for other measures that, for example, the log loss, this is less useful for a single method. So log loss 0 means that the system works perfectly, but this practically never happens. So you don't have really an upper bound because a system which is very confident in the wrong answer gets very high log loss. And then so you have one single value there for your data set, and this doesn't tell you very much. So it is useful when you compare models. You have 2, 3 a number of systems, and you look at them. The one with the lower log loss is the better from this point of view. So it doesn't mean that it will have better accuracy at some sort of like some selected operating point, or also that like end users would be most accepting of that system with the lowest log loss. So, okay, how, now we get to the interesting part. So metrics are rather easy. So you just might wonder, okay, so what is the fuss then about the reproducibility? Isn't reproducible research just like, okay, you have access to the data, you have access to the code, they are openly public, and all you need to do, it's like, okay, you do consistent measurement. So of course, what is consistent measurement? You should use the same metric, which like, wow, yeah, you didn't see this one coming. But so there are some details here which can kind of ruin your day. So they are mostly related on how the data is organized in the experimental setup. So this relates very much to the previous talk. So one little detail that can deceive you very much with the performance is the cross-validation setup. So how do you create your folds and what kind of data you place in your training and in your test and how? And then the other one is kind of how the metrics are calculated over these folds and over the classes. So, okay, this k-fold, you are probably familiar with the process, how to create a number of folds. We do this when we want to have more test situations. So it's like we have more data to test on. So the general process goes like, we take the data, we split it randomly in a number of groups, then we take each group as a train set, and then everything else is for training, and then we rotate. So we train and we test the models for each of these combination, and then we kind of like calculate the performance. This is like, okay, we evaluated how it works. Okay, that sounds pretty straightforward, but I have this nice example for you. So let's say we want to do acoustic scene classification. We have recorded some audio in the airport and in a restaurant in 3 different cities. So we have Helsinki, Paris, and Rome. So the shape is the city and the color is the acoustic scene. We do a random split to keep, we want to keep like 30% of the data for testing. And then we end up with something like this, like 30% is in the test set. The other things are in the train set. We train the model, we test, we evaluate the result, and then the system says, okay, 97% accuracy. Wow, excellent. This is a very good system. So now the question is, did this model really learn the acoustic scene characteristic? So remember that that is the color of the items. Or was the system helped by the actual characteristic of the city? So that would be the shapes. Because here we had in the training all the shapes of all the colors. So we cannot say for sure that if we go to record in airport and restaurant scenes, like, I don't know, in Berlin, the system would be able to recognize them with 97% accuracy, right? So in order to make sure that we teach the model the acoustic scene, we would want to do a controlled split of the data. So we separate the shapes. We keep 2 cities in the training, and then we put the 3rd one in the test. So we get this kind of a setup, like on the right-hand side. And let's say with this setup, the performance would be 78%. So it's much lower than the other, but this can be trusted that when using it on some unseen data, we might obtain some more or less similar performance. So this is referred to as generalization. So the generalization does come from the models, so like from the machine learning part itself. But the problem is that the wrong measurement can give a very false impression about the system capabilities. This is kind of an important thing here. And okay, this was a rather crude example. So in fact, this kind of like, I call it contamination. This kind of contamination is actually much more subtle in our work. So in some cases, it can be actually very hard to think of all the factors that can cause it. So when we work with audio, longer recordings are cut in shorter clips for various reasons. So maybe we need to distribute them easier, or maybe we need to remove some parts, like for example, for privacy reasons, we need to cut away some speech. Maybe we want to isolate some sounds from a longer recording. So the thing is that it's very important to keep and use the information about the original recording. So for example, we have recorded acoustic scenes. We made a few recordings in the same place. And then we cut everything into segments of 10 seconds. So we might have, for example, 60 short clips that originate from the same exact spot in a time frame of like 5 minutes. They are definitely very correlated. So maybe I should be careful to put them all in the training set or all in the test set, but not like split them half and half, because that will give me this kind of a fake high performance for my system. So the same way it happens in other kind of like audio classification tasks. For example, any individual sounds which are produced by the same source will be very similar. Like if you knock the same door 50 times, it's just still the same door. Individual notes of an instrument from a longer musical phrase. So like if it's the same piano, it's the same piano. If you care about recognizing the notes, it's a different story, but then otherwise it's the same source. Then something from music information retrieval is this so-called album effect. Is like from a long time ago. So like when songs from the same album, they contain some common characteristics which are related to the post-production. So not to the music itself, but the way it was kind of like processed for the album. So then you should have like okay, when doing artists classification, then the one album of the artist should be in training and the other album should be in the test. Otherwise, yeah, you might recognize something else. Okay, so the thing is that this gives you over optimistic results. And it is very important that, of course, everybody uses sklearn, but you should know that this stratified k-fold in sklearn does not know such details about the data. So it does split them nicely, it tries to make the balanced folds and everything, but I would say that you should be suspicious if you get too high accuracy, too high performance. So I can give one such example, which was extremely hard to figure out for us. So we started doing sound classification like 2010. So back then it was very hard to get hands-on data. So we paid to some website which was collecting like sound effects for movies. And so we downloaded from there a bunch of files. We paid some amount of money for each file that we downloaded. So we get hundreds of files which were containing isolated sound effects. So we split them, we do training testing, excellent. So we get very good results. Suspiciously high, as I say, because for classifier, which was back then like GMMs and MFCCs and over 60 classes, and then it was like, wow. So at some point we realized what was the problem. It was exactly this contamination. They recorded the sounds such that there was like a sequence of the same sound in the, like it was long recording, multiple instances, and then they cut them into the pieces. We had no way of knowing that because we just downloaded the isolated examples. But then we actually figured out somehow that in the names of the files, there was some sort of relationship. So like some characters in the name of the files were revealing kind of like the original recording. So then when we resplit and we took care of that, then it started behaving more like what we would expect. So yeah, I think that just if you just get suspiciously high performance or some like suspiciously high improvement over another study that you are comparing yourself with, check your data. Check the data. Okay, then we have this averaging, data balance and averaging options. So these are actually two different things, but they have a similar effect. So let's say we have here 3 classes, which are of different size. And this is our test data. We test the system on this. So for class A, our system gets like 95% correct of 100. For class B, it gets 5 of 50. And for class C, none of the 10. So again, I'm just giving accuracy as example because this is very easy. So for class A, we have like 95% accuracy. Then for class B, 10%. For class C, 0. So if we average this, our system gets an accuracy of 35%. This is bad. But if we count the items instead of looking at the class, we just want to know, like the output, is it correct or not? So the system actually classified correctly 100 of the 160 items that we gave it. So this is then an accuracy of 62%. So which of these two values is the correct one? Okay, so this is the thing. It depends what you want to measure. Do you want to know how the system behaves overall, or do you want to know how the system behaves for the different classes, because you see, like for classes B and C, this is like very bad, this system. So then this overall count is dominated by class A. Yes. So these are called, so, okay, it's officially like macro average and micro average, but I like to think of them like, okay, class-wise and instance-wise, because this is much more informative in a way to say, okay, when you calculate class-wise, first you go and you calculate the performance for each class, and then you do the average versus counting them one by one. So this kind of like, this is always a problem when you have unbalanced data, and then it happens very often because especially when you do some splits in a controlled way, or like you just go and record some data, you might have this kind of data imbalance, and it's often between the different folds. You will have like in one fold more data of one class than in the other. So kind of like when you resplit a data set, you might have different kind of distribution of the data of the classes in your folds, and then this will be something else. You measure performance on a different kind of test set. So if you try to, well, reproduce, I will use the word reproduce, someone's method, and the only information you have is that somebody used 5-fold cross-validation, you actually do not know what was in those folds. So this is kind of like, yes, do save, do keep track of what data points go where. Because depending on the data balance, you might end up with extremely different performance. So one thing that you can do here is that, okay, you can use instance-wise averaging so that you don't look at the classes. But then the better part is to actually not do the evaluation of each fold and then do the average over the 5 folds, but you kind of run all the train and test experiments. So you train, you test, and you have the system output for your first fold, then you train and test and have the system output for the next fold. And then when you have run them all, you have practically the answers of your system for all the data. And then you can calculate the performance, because this way you avoid this kind of like a problem of having some sort of an imbalance between the different folds. Okay, of course, this requires that everybody does the same, but I would say that, okay, take it as a best practices. Okay, so I have one more example, which is specific to sound event detection. So we have proposed 2 different ways to count these intermediate metrics for this contingency matrix. So segment-based and event-based. So I'm not going to go into the event thing. So just like for the segment-based metric, what we do is that we compare the system output and the reference in some short time segments. So we have this kind of information on what sources are active, that's the color, and when they are active. So there is a start time and then an end time for the different sound instances. And then in between, this is like a one event. But if we split, let's say in 1 second pieces, then we have this one sound being active in multiple of these kind of segments. So first thing that we do, okay, so this is like the step-by-step going through the evaluation. So first thing that we do is like we just associate, we give like a binary indicator per segment. So in 1 second, do we just say, is this source active here or not? So the reference says yes, 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 yes for the first class. And then the system output goes the same way. So this is kind of like a binary indicator matrix for the activity of the sounds with the desired temporal grid. And then we do the comparison one by one in these segments. So then we count like true positives, false positives. Okay, yes, we have both the reference and the system output say the same thing. So we have the true positives, the false positives, true negatives, and then the false negatives. And this is our kind of comparison. And then let's say we calculate F-score in this one. We go class-wise, and then we calculate how many, for the first class, we have 4 true positives and no errors and so on. Then we can have like precision recall. So in the first line here, we found everything correctly. So we have like a 100%, F-score is 1. This is very nice. Then for the second one, for example, we didn't find any relevant, like everything was errors. So if we average it, this is like 0.53. So this is the class-based averaging. But then if we do it with the micro average, the instance-based, then we just sum everything up. So we look at the entire thing here. And then we get the F-score of 0.69. So this is much higher. So this is also in a way, let's say, maybe a false better performance because it's the same system. But this other, when you consider instances, then you look at how the system is generally behaving in time. Like, does it kind of find most of the parts where different sounds are active? And then if you go look at the class base, then you are like interested really, okay, it mostly finds the first class and doesn't find anything from the second and the third. But okay, this is even more annoying. So the error rate. So in the error rate, we measure errors. So the false positives and the false negatives, they are insertions and deletions. And the pair of them is a substitution. So the same way they measure in speech recognition, for example, word error rate. So when the system substitutes one word for another. So this is like consider it's only one mistake, even though actually what happens is that one word is missing and another one is inserted. But this is like considered there's only one mistake. And then we count all errors and then we divide by the total number of active events there. So, okay, this is the same kind of like a colorful bit with the intermediate statistics. And here we actually have to look in each segment. So for this segment K, we have like one substitution because here we have like a one false positive and one false negative. That is like a one substitution. And then we still have like one false positive there left. So there's one more error and so on. So we look that way. And then we calculate the sum of all these errors. And then we get an error rate of 0.38. So here you actually notice that the error rate, this is not defined the same way if we want to calculate it class-wise. Because if we want to consider only one class, if we just go like on a line, we will not have any substitutions. We cannot count substitutions. So we can count only insertions and deletions for a class. So in a way, if we do it class-wise, we penalize the system twice for one substitution error, so what I'm trying here to kind of tell is that in this case, for the error rate, the micro and the macro averaging options, they are even further apart. So here they are conceptually further apart. Like for the F-score, it was only kind of numerically. They mean the same thing, but here they are even different. Yeah. Okay, sorry, this was left over. I'll skip that. So which metric is best then? Accuracy is very nice because it's a very simple measure of the ability of the system to take the correct decision. But you have this disadvantage that if you have a lot of like a true negatives, then you might have like a huge accuracy, even though your system maybe this doesn't find anything. Then, for example, F-score, this is widely known, this is easy to understand. But then the choice of averaging is especially important because always here also the large classes will dominate the small classes. So the system behavior on the larger classes will influence the number if you do the instance-based averaging. So do you care about the overall system behavior or do you care about like a single class? Okay, so area under the curve, this is nice because it allows comparison of the classifiers, but this is generally, I wouldn't say it can only be applied to binary, it is generally applied to binary classifiers. The generalization for the multi-class problems, they are not so well defined. They are generally doing like the average of the area under the curve per class, but then again, okay, here we have no choice then for the averaging. Okay, and then there is the log loss. So this is very nice because you have an idea of the classifier uncertainty and you don't need to have any threshold or decision, but this is only useful to compare models on the same data. You want to see the behavior on the same data. So it's kind of like very tied to the experimental setup. Okay, only a few words about statistical significance. Yeah, it was mentioned that we are not so good at statistics, but the one thing is that results produced with the GPU are generally non-deterministic unless you really fix your seed. So like, otherwise there's always a small difference. It might not matter, it's like very small really. But then the other thing is like, always when you write a paper, or always when you, like any paper that you read, there will always be one way or another said, the proposed system outperforms the current state of the art or some other system by this much. So what amount of difference in performance matters? So the answer is actually that it depends on the amount of data, so on the sample size. And this is why you want to check a bit, is it really statistically significant? So it's good if you can do hypothesis testing, and then, for example, for the classifiers, I like this McNamara test because it kind of tells if the system, if the two systems, even if they have very, very close performance, if they behave differently on the hard to classify samples. Then the other option is to calculate the confidence intervals for the metric, because this depends on the size of the sample, how much data you have there. And you can find different methods depending on what you can assume about the metric. So like the simplest is with this binomial. If you just have like for accuracy, it is very simple to calculate. And then you can tell, okay, if your system is 2% better than the other one, it matters, or it doesn't matter. It's like, okay, they are pretty much the same. This is kind of like in 2018 we have edited the chapter in a book, and there was like about data sets and evaluation, and there were the 5 points for devising evaluation protocols. So okay, what task, what you are classifying, or like what you are doing, so like it should be something useful, of course. Research is always like that. Then the data amount, like you should have a lot of data. Of course you should have good data, but you should have enough data. This is one thing. Then try to find a significance test that can be applied there, because then you can understand what kind of improvements you are getting. You have to compare against a well-established technique. So you need to have some sort of baseline system. This is often like the, okay, when you are, if you just start something, you have some new data and you try some new problem, then it's you are the baseline system. So then it's hard to compare against some well-established technique, but then you can at least have some vanilla implementation of something to show that what you're doing is like more sophisticated, and this is why you get the higher performance. Then the choice of metric, this is also important. So you choose the metrics that are emphasizing what you care about. Related to this one is the fact that you should do some sort of error analysis, especially for real applications. The errors are not all equal. In some cases, it's more acceptable to have false positives than false negatives. So it depends where you draw the line for this. Okay, so this is my last slide, and this is in a way my 2 cents on like what reproducible research should be. So this kind of recaps a lot of elements from also Brian's presentation. So you want to use an open data set, or you publish your own data set. And so there are data sets available in services, like, okay, we mostly put them on Zenodo. And you want to look for data sets which are kind of nicely documented, and if possible, they should be introduced like with a scientific paper. So like have a paper, a baseline system, and a cross-validation setup. So there is the data, there is the code, and then there's the evaluation. So you should release your system if you can to allow reproducing the results from your publication. So you use this data, which is available there, and then if you are creating some extra bits, like, yeah, you will never explain all the details in the paper. So if possible, then you release your code and then everything's like at least there. And then you should report your results in a uniform way. So if you are improving upon an existing system, then you should report the same metrics using the same data set, using the same cross-validation setup, which is kind of clear. If you publish your own data, then you should publish your cross-evaluation, like your cross-validation setup, so that other people can use the same and do it this way. Then, of course, use some established metric implementations if you are not releasing them. So, of course, you can use just the basic metrics from the scikit-learn if you explain clearly how you are using them. Then we have the SED eval, there's the PSDS eval, there's the MIR eval. I apologize, I forgot to put it here. So the thing is that everything, all these different bits should be very well documented. Maybe it's a bit, I think it's quite difficult to actually document everything and have everything completely, such that somebody who takes it will be very easily reproducing your results. But at least you have to try. Like, yeah. Yes, this was my last slide. So thank you very much. And now for the questions.
Okay, thank you, Annamaria, for this guidance into the jungle of metrics. Do we have any questions from the audience? So you can write them in the chat box or raise your hand and speak. So, well, if I will ask one question. For me, as a, let's say, an individual, I have my pool of metrics, and I kind of, let's say, know how I have an intuition on how they behave, and I use them some kind of as beams in a distillation process to understand how the algorithm I'm studying is behaving depending on the data. You have a long experience on something which is more on the community basis with the decades challenges, where basically people submit a system and you compare them with a wide array of metrics. What is your experience on the community use of several metrics?
Yeah, this is kind of a difficult thing, because this is why it matters what you measure, and your application practically dictates what you should measure. So we have a lot of systems that people are submitting their system output, and we are doing the evaluation, and then we are publishing various metrics, and they are not always correlated. So then we usually we just simply make a choice, like a crude choice. Okay, we're going to use this metric for ranking the systems, and then okay, this is the best system. But this is the best system from the point of view of, like we were calculating, for example, error rate for the sound event detection. If you look at the F-score, they are in completely different order. So then the question is, okay, so what is the best system? This is why we don't want to say that, you know, like the winner of the challenge, because there is no winner. We are all the winners, but it kind of, it is ranked first if you look at the error rate. So, yeah.
Yeah, it's not an easy question. Yeah, and there is no definite answer, I guess. Is there any other question from the audience? Yes, Brian, go ahead.
Hey, thanks for the talk. I really like a lot of the points that you made. One question that I have is, you mentioned the scale of data matters here, especially when you talk about statistical significance. And for some data sets, it's relatively, or for some problems, it's relatively easy to get large quantities of data, and others, it's really not. And I'm wondering if you could talk a little bit about how that affects the choice of, say, cross-validation versus a pre-registered train test split that everyone agrees on, right? So for very large data sets, maybe you don't need to cross-validate so much, but I'm wondering what your experience with that is, especially in DK's land.
Yeah, DK's land. Yeah, we have exactly the similar kind of situation because, for example, we have this acoustic scene data and it has about 40 hours of data. And then they are split into pieces of 10 seconds. And then there's thousands and thousands of examples, which we kept for the evaluation set. And that is like, okay, we consider that this is enough. And then we just do the one split. And okay, this is your training data, this is your test bit which you can use during the system development, and then there's some other like secret data. So for that one we do not have any faults, but then for example we have the sound event detection data, and because annotating with this kind of like onset offset for everything is like super slow. So in that one I think it's like 2 hours. So with 2 hours of data you need to, so you pretend you have more data, because otherwise if you split it, then what do? You have an hour and a half data for training and then a bit for testing. So then you're going to do this rotation to pretend at least that you have 2 hours of test data. But that was one very big problem, for example, for balancing, like, okay, it's completely unbalanced in the folds, because you have a recording, which is like 3 to 5 minutes long. And there are multiple classes and multiple instances in that file, but you have, this is one of your clips and you have to put it in testing or in training. So you are somehow squeezed with how you're gonna, you cannot balance the classes, because for example, what if in one of the files you don't have at all, I don't know, bird singing, and that is that class is part of your target classes, but then it's like, so what you do, you have this file which doesn't have this sound at all, and you have to put it somewhere. Yeah, so this became like a very big problem in this like how you fit as best as possible how you combine them such that you can rotate. I think the simplest way is to do the leave one out, that you like one file is the test and the other ones are for train. But this is all, it doesn't always work, because this is what I was just giving the example. If some class is missing, then it does not have any meaning. Yeah.
Thanks.